All right, welcome back. Today we've got the 9.3 notes solving and evaluating with common bases. These notes are going to be very similar to 9.2 with two main differences. There's one new topic, which is very simple. We'll get to that towards the end. And then the other thing, it's very similar to 9.2, just the algebra is going to be a little bit harder here. Okay, so other than that, it's going to be pretty familiar stuff, hopefully. All right, so we're mainly going to be solving exponential equations here, which is an equation where the variable occurs in the exponent. We saw these yesterday or last time on 9.2. The only difference was we found those, we saw these types of equations on our second step. After we put something from log form into exponential notation, then we saw those equations with exponents in the variable. I'm sorry, variables in the exponent. Said that backwards. All right, so the main idea is right here, and we talked about this yesterday. If b is a positive number other than 1, because 1 to any power is always 1, so that would kind of make this a pointless equation here. These two things are going to be equal, so something other than 1 raised to the x equals something other than 1 raised to the y. Those are going to be equal if and only if x equals y. And they give us an example here. So if 3 to the x equals 3 to the 5th, then x has to equal 5. But yeah, that should make sense because, sticking with the same base here, if I have 3 raised to some power, and that's equal to 3 raised to some power, well then, since these are equal, what's the only way that these two, this thing is going to be true? Well, since my base is already matched, then my exponents would have to match. So then, yeah, this would have to equal that. So if this is x and this is y, x would have to equal y, and that's what they're saying over here. Okay, so anyways, we looked at that last time. We're going to be looking at that idea again today. The algebra is just going to be a little bit trickier. All right. All right, let's just dive right into the examples here. Let me zoom in since we don't need a ton of space for each example. All right, so they want us to solve 3 raised to the x equals 1 over 81. Okay, now again, we saw these types of problems last time, but last time they started in log form. So if this was in log form, we'll put it up here where we have a little bit of space. This would have been log of 1 over 81 base 3. That's how this equation would have started. We could have, if we wanted to, added equals x, and then we know it's our base to our power equals that thing. Okay, so they put it in exponential notation for us, and this whole first section is done like that. Okay, so then we'll see some more log problems later on, but here we're just dealing with exponential notation. And then how do we solve this problem in exponential notation? Well, like we talked about last time, we want to get a common base. Okay. Now, when you're trying to find what your common base is going to be, look at the smaller number because it's often going to be the smaller number. For example, can I write 3 as a smaller number raised to a power? Well, no, it just doesn't work. So then that's most likely going to be my base, 3, and then I want to see, well, can I write this number as 3 to a power? And when you're trying to write this as something else raised to a power, ignore any fractions or radicals or anything like that. You just want to focus on the numbers. So I got 3 and 81. Can I write those both as 3 to a power? Well, sure. This is already 3 to a power, so great. I can leave that alone. 3 to the x equals, and then how can I write this thing as 3 raised to a power? Well, first of all, how did it become a fraction? When do we flip our problem? When we have what type of exponent? A negative. And then 3 to what power gives me 81? Well, that's just 3 to the 4th power. And then now that I have 3 to a power equals 3 to a power, well, then I know my exponents have to be the same. So I can ignore the bases. So they don't cancel out. I don't have to cross them out. I can just ignore them. I know that this exponent has to be equal to that exponent. So then we get x equals negative 4, and then we're done. So that's our answer. All right, let's take a look at the second example here. All right, so again, this is already an exponential notation for us. Awesome. Now I want to get a common base. Well, let's start with the smaller number 2. Since I can't rewrite that as something else smaller to a power, then I'm assuming that my common base is going to be 2. And can I write that thing as 2 to a power? Well, sure. 8 is just 2 to the 3rd power. So then this is already 2 to a power. Great. I'm going to leave that alone. Although one thing we can do is distribute that negative up here. So we can write this as 2 to the negative x minus 3 equals, and then I'm going to rewrite 8 as 2 to the 3rd. So there's a lot of number manipulation here. Okay, again, I'm just manipulating this number to make it look different, but I'm not changing its value. Instead of 8, I'm replacing it with something equal to 8. Instead of 1 over 81, I'm replacing this with something equal to 1 over 81. Okay, so we're just rewriting numbers in a different way but not changing the value. Okay, and then now that I have 2 to a power equals 2 to a power, well, now I know that these exponents have to be the same, so I can set these equal to each other. So I know negative x minus 3 has to equal 3. Okay, to solve this, add 3 to both sides. And I get negative x equals 6, so then x equals negative 6. And that's our answer. All right, moving right along. Next one, 4 to the x plus 2 equals 2. So again, look at the smaller number. Well, I can't rewrite that as something smaller to a power. So then I'm assuming my base is probably going to be 2. Can I write this thing as 2 to a power? Yeah. So then we have 4 raised to the x plus 2 equals 2. Okay, and then how are we going to rewrite 4 with a base of 2? Well, I'm going to write that as 2 to the second power, so 2 squared. Okay. Next, and remember this is a binomial right here. When I have a power raised to a power, in other words, when I have parentheses between two numbers, well, what do I do with these numbers? When we multiply. So we got to remember our exponent rules. If I multiply those, I get 2 to the 2x plus 4 equals 2. Now, one thing you want to remember when you have just a whole number like 2 here, well, that's the same as 2 to the first. Okay, because if I don't put that 1 there, well, then I want to set 2x plus 4 equal to what? Well, there's got to be something there, so we'll go ahead and write a 1. Okay, so again, now we have 2 to a power equals 2 to a power. Well, now I can set my exponents equal to each other and then solve. So we get 2x plus 4 equals 1. Okay, next, we want to subtract 4 from both sides. That gives me 2x equals negative 3. And then if I divide both sides by 2, I'm not writing that step because it's taking up space. But if I divide both sides by 2, I get x equals negative 3 over 2. All right, and then that's my answer. And then don't forget, you can always plug your answer back in and check to make sure that it works. Okay, some are easier to plug in than others, but it's a good idea to check. All right, moving right along. Got a few more to go of this type. All right, next one, 7 to the 2x equals 49 to the 3x minus 2. So here we got x in 2 spots, but that's okay. We'll combine them eventually. First thing we want to do is get our common base. So what's our common base going to be between 7 and 49? Well, again, focus on the smaller number. Okay, I can't write this as something smaller to a power, so then I'm guessing my base is going to be 7. And yeah, I can write that as 7 to a power, so then my base is going to be 7. This is already 7 to a power, so leave that alone. Equals, and then again, we've got 49 to the 3x minus 2. Okay, but instead of 49, we're going to write that as 7 squared. Okay, now I just want to simplify this, just like the last problem. I want to multiply this stuff. So I get 7 to the 2x, that stays how it is, equals 7 to the, and then multiply the 2 with the 3x minus 2, and we get 6x minus 4. All right, and then now that I've got 7 to a power equals 7 to a power, well, now I know my exponents have to be the same. Those have to be equal, so I can set those equal to each other, and we get 2x equals 6x minus 4. All right, now I want to get x by itself. Let's do two things at once here to save a little bit of writing. I want to add 4 to both sides. And then while we're at it, we'll subtract 2x from both sides. Okay, so then those cancel and those cancel, and then I get 4 equals 4x. And if we divide both sides by 4, we get x equals 1. Okay, and again, plug it in and see if that actually works. In fact, we can do this one pretty easily in our heads. If I plug in 1, 2 times 1 is 2, 7 to the second power is 49. Okay, so I get 49 on the left, and then if I plug in 1 here, 3 times 1 is 3, minus 2 is 1, and then 49 in the first power, yeah, that's also 49. So it does work. So we didn't do it on the other ones, but keep in mind, if you're ever unsure about an answer, plug it in and check. All right, 2 more to go in this section. All right, here we've got 81 to the x minus 3 and 1 over 3 to the 5x minus 6. Okay, so again, the first thing we want to do is find our common base. So ignore any fractions or exponents or radicals if you have those. We just want to focus on the numbers. So I got 81 and I got a 3. Okay, how can I write those with the common base? Well, I can't rewrite 3 as something smaller to a power, so hopefully it's going to be 3 to a power. And then, yeah, like we saw on the first problem of this page, right up here, 81 is just it's 3 to the 4th power. Okay, so we can use a base of 3. So then I want to write this as, instead of 81 to the x minus 3, well, 81 is 3 to the 4th power. Equals, and then instead of 1 over 3 to the 5x minus 6, how can I rewrite 1 over 3? Well, that's going to be 3 to the negative 1, because I want to flip it, but then leave it a 3. So I'm going to raise it to the negative 1 power. Okay, now I want to multiply my exponents on both sides of my equation. So let's see, 4 times x minus 3, I'm going to get 3 to the 4x minus 12. And then on the right side of the equation, I'm going to get 3 to the negative 1 times 5x minus 6 gives me negative 5x plus 6. All right, so now we've got 3 to a power equals 3 to a power. Now I can set my exponents equal to each other. So we get 4x minus 12 equals negative 5x plus 6. All right, let's do a couple things here. First, I want to get my x's on the same side of the equation. I'd like to keep them positive if possible, so I'm going to add 5x to both sides. And then at the same time, let's go ahead and add 12 to both sides to get my numbers on the right side of the equation. All right, and then that's going to give us 9x equals 18. And if we divide both sides by 9, we get x equals 2. All right, and again, you can always plug that in and check, but that is the answer. Let's go on to the last one here from this section, and then we can move on to a little bit different type of problems. All right, so here we got 5 to the x equals 5 times the square root of 25. Okay, so this time we've got 3 numbers to deal with. We got 5 and 25. Okay, that's okay, as long as we can get a common base with those 3 things. What's my common base going to be between 5 and 25? Well, it's going to be 5. So I want to write everything as 5 to a power. This is already 5 to a power. Great. This is already 5 to a power. I just got to write it as 5 to the first times. And then how can I rewrite the square root of 25? Okay, now there's different ways you can do it. I can write it as 5 raised to the 2 over 2. Okay, or what is the square root of 25? Well, it's just 5. Okay. And then here again, we have some options. You can think about this different ways. I'm multiplying 2 things with the same base. I can add the exponents. Or since it's just 5 times 5, well then we can just rewrite that as 25. Okay, but if I rewrite it as 25, well then I'd want to get a common base of 5 again. So then I'd have to rewrite it as 5 squared. So let's just do what we said the first time, use our exponent rules. Since I'm multiplying 2 things with the same base, we'll add the exponents. So then I get 5 to the x equals 5 to the 2nd power. Okay, and then now that I've got 5 to a power equals 5 to a power, I know my exponents have to be equal, so we get x equals 2. Okay, so sometimes you're going to have to combine 2 numbers and get them with the same base. Like on this problem, we'll see more examples like that very soon. Okay, but this one, just x equals 2. All right, at the bottom of the page, now these are more like what we were doing yesterday. We actually have a log problem. Okay, so the first step to solving a log problem is writing the equation without the log. Okay, so we want to write it in exponential notation. So how do we do that? Well, just like we did last time. First of all, we can say, well, this is going to equal something. We can put equals x in there. And then remember, your answer to a log problem is your exponent. So it's always my base to my power equals that thing. So then on this problem, we get 9 to the x equals 27. All right, now it's just like the previous 6 problems we just did. Now that it's in exponential notation, now I want to get a common base. Okay, so let's see, can I write 27 as 9 raised to a power? Well, it's 9 times 3, but no, it's not 9 raised to a power, at least not a whole number. Okay, so then what we want to do here is rewrite both of these things with a smaller base. Occasionally we'll have to do that as well. What can I rewrite 9 and 27 as? What smaller number raised to a power can I get a 9 and a 27 from? Well, 3. So then instead of 9 to the x, I want to write 9 as 3 squared to the x. And then instead of 27, I want to write that as 3 to the third. Okay, so again, it's just manipulating those numbers, writing something with the same value, but making it look different. Okay, this is going to give me 3 to the 2x equals 3 to the third. And then now that I have 3 to a power equals 3 to a power, well, now I can ignore my bases and set my exponents equal to each other. So I get 2x equals 3. And if we divide both sides by 2, we get x equals 3 over 2. Okay, and again, plug it in and see if it works. If I plug it in here, if I raise 9 to the 3 over 2 power, okay, well, the 2 is on the bottom, so then I want to take the second root of 9, which gives me 3, and then I want to raise that to the third power, which, yeah, that gives me 27. So again, you can always plug in your answer if you're not sure if you got it right. All right, one more on the front page here. Okay, same type of problem, just a little bit tougher algebra on this one. All right, so the first thing we want to do with this log problem is write it without the log. So again, this is going to give me some answer, so I'm going to put equals x, and then to put this in exponential notation, it's my base to my power equals that thing. So we get 7 to the x equals 49 times root 7. Okay, so this is kind of like that problem we did up here, where I want to write all three parts with a common base. So what's my common base going to be between 7 and 49 and 7? Well, it's going to be 7. This is already 7 to a power, great. And then how can I rewrite 49 as 7 to a power? Well, that's just 7 squared, and then times the square root of 7. Well, the square root of 7 is the same as 7 to the 1/2 power. Okay? All right, awesome. Next, before I move on, well, I need to combine these two things because I want 7 to a power equals 7 to a power, not 7 to a power equals 7 to a power times 7 to a different power. So I have to combine this right side here. Okay, so just like we did on the 6th example, since I'm multiplying these two things with the same base, I want to add the exponents. Okay, so we get 7 to the x equals 7 to the 2 plus 1/2. Well, 2 plus 1/2 is 5.5. I'm sorry, I'm thinking ahead. It's 2.5, which we can write 2.5 as 5 over 2. Okay, so we want to get a common denominator between 2 over 1 and 1 over 2. Add those together, and we're going to end up getting 5 over 2. I'm just going straight to the answer since we don't have a ton of space left. But now that I have 7 to a power equals 7 to a power, then we get x equals 5 over 2. Okay. All right, and then just in case anyone needs it, to add this part together, we got 7 to the 2 plus 1/2. We can think of that as 2 over 1 plus 1 over 2. Well, that's the same as 7 to the multiply top and bottom by 2. I get 4 over 2 plus 1 over 2. And then that's how we got 7 to the 5 over 2. Once I get a common denominator, I can add the tops. So that's where this came from. All right, so kind of a lot of examples, and it's similar to what we did last time, but we're finally getting closer to the new stuff. All right, a couple more examples at the top here. Evaluate each logarithm, so we want to do it the same way. Again, these are just a little bit, these are good examples to have because the algebra is a little bit harder. All right, but to do this one, well, first we'll say it's going to equal something, and then I can put it in exponential notation. And also, if you can look at this problem and see what the answer is, then great, just write the answer down and you're done. But if I want to put it in exponential notation, it's going to be 1/2 to the x equals 32. Okay, and then here I want to get a common base. So again, ignore the fractions or radicals or exponents. I look at your numbers, 2 and 32. What's my common base have to be? Well, 2. I want to write both these things as 2 to a power. So let's see. This would be, instead of 1/2 to the x, I could write that as 2 to the negative 1 to the x equals, and 32 would be 2 to the 5th. Okay, we'll go up here where we have a little bit more space. And then let's say I got to multiply these, so I get 2 to the negative x equals 2 to the 5th. And then now I can set my exponents equal to each other. Negative x equals 5, so x equals negative 5. Okay, and again, plug it in and check. If I plug in negative 5 here, yeah, I would flip it to make it a 2, and then raise it to the 5th power, which would give me 32. So we know it's correct. All right, one more of these, and then problems finally start getting different from last time. All right, so we'll start off by saying it equals something. We'll call it x, and then I want to put this in exponential notation. So it's my base to my power, so 11 to the x equals the cube root of 1 over 121. All right, and then what's my common base going to be? Well, it's got to be 11 because I can't write this as something smaller to a power. And then, yeah, this is just 11 squared. So my common base is going to be 11. So then I get 11 to the x equals 11 raised to the, let's see, we've got a couple things going on here. First of all, anytime we have a radical, we know that our answer is going to be a fraction. Okay, let's do the fraction part first. I want to take the cube root of that thing. Well, like a tree, roots are on the bottom, so then it's going to be a 3 down here. And then I need to get 121, and I can get that by squaring 11. So I want to raise it to the 2/3 power, but it's also a fraction. How did we flip this and make it a fraction? Well, then I had to have a negative exponent. So then we get 11 to the x equals 11 to the negative 2/3 power. And then now that I have 11 to a power equals 11 to a power, well, then I know my exponents have to be the same. So then we get x equals negative 2/3. So not a lot of algebra to do here, but kind of a tricky one to write as 11 to a power. This big old mess here. All right, so finally moving on to some newer type problems. Okay, they're not going to be super new right away. Like it says here, we've already performed one type of solving problem, convert from log form to exponential form. Okay, now it says solve for x. Really, we're doing the exact same thing. Okay, the only difference is here, our x is in a different place. Now we know the exponent, I got to find this thing. I got to find this x here, I got to find this x here. Okay, so we're not always looking for the exponent. They can move that variable wherever they want it to. Okay, but in a minute, you're going to see the problems are going to start to look different like they are down here. Okay, but really with these log problems, you're going to see two types of problems. Excuse me. You're either going to see logs on both sides of your equation like this, or like what we've been seeing, logs on one side of the equation. And when you have logs on one side of the equation, it doesn't matter where your variable's at, you do it the same way. You write it in exponential notation and then solve what you have left. So let's take a look at this problem. So again, we do it the exact same way we did the last couple problems. It's my base to my power equals that thing. So I get 9 to the 1/2 equals x. Okay, great. I've already got x by itself. We don't really have to do any more solving. We just have to simplify. What is 9 to the 1/2 power? Well, that's the same as the square root of 9, so I get x equals 3. And that's it. Okay, so anytime you have log just on one side of your equation, always put it in exponential notation. So that's why it's important to know how to put it in exponential notation. Okay, same thing here. It's a binomial with x in it. Who cares? Do it the same exact way. It's my base to my power equals that thing. So we get 4 to the 3rd equals 5x minus 1. Okay, well, let's simplify this first. 4 to the 3rd is 64, so we get 64 equals 5x minus 1. Now I just got a simple algebra problem that we need to solve. So we'll start by adding 1 to both sides. And we get 65 equals 5x. And then if we divide both sides by 5, we get x equals 13. So again, anytime you see only one log in your equation, always do it the same way. Put it in exponential notation and then solve. Okay, all right, here, remember natural log just means log base e. So then my base is e, so it's going to be e to the 1st power equals that thing. So e to the 1st equals x minus 4. All right, important question. How many variables do we have in this equation? Just one, x. Remember, e is a number, kind of like pi. Okay, so just leave that in your answer. And then just focus on x. We want to get x by itself. How do I get x by itself here? I'll just add 4 to both sides. And then I get x by itself equals, and then over here, this is just going to be e plus 4. Or 4 plus e, the order doesn't matter. It's kind of like pi plus 4. Okay, same thing. So there's our answer. So some of your answers are going to have e in it. That's okay. It's just a number. All right. So finally, moving on to something a little bit new here. I know it's been a lot of examples of stuff you already kind of knew. Okay, but if we get a problem like this, log of something base 5 equals log of something base 5, well, how do we solve this? Well, it's the same idea as this. If I have 2 to a power equals 2 to a power, well, then I know that my exponents have to be the same, right? Otherwise, these wouldn't be equal. So if I have, 2 to the x equals 2 to the third, well, then I know x equals 3. Well, same idea here. If I have log base 5 of something equals log base 5 of something, well, then I know that these two somethings have to be the same. Otherwise, these wouldn't be equal. Okay, so when I get a problem with logs on both sides of the equation, once we get it down to where there's one log on each side of the equation, because eventually that'll be a task, then I could ignore the log base 5 part, And I know that 4x minus 7 has to be equal to x plus 5. Okay, and I can do this as long as my bases are the same here. And if they're not, it's probably a typo in this chapter, so just let me know. Okay, and then now we just want to solve this equation. If I subtract x from both sides, and while we're at it, let's add 7 to both sides. And that's gone, and we get 3x equals 12. So then divide both sides by 3, we get x equals 4. Okay, and again, if you're not sure about your answer, plug it in and check. If I plug in 4 here, 4 times 4 is 16, minus 7 is 9. If I plug in 4 here, 4 plus 5 is 9. So yeah, when x is 4, I get log of 9 base 5 on both sides of my equation. So yeah, those are equal. Okay, so again, anytime you have just one log in your equation, it could look something like this, or it could look something like that. We put it in exponential notation and solve. If I have 2 logs in my equation, well, as long as my bases are the same, and I have 1 log on each side of the equation, well, then I could ignore the log in the base part and set that part and that part equal to each other. All right, 2 more examples to go, then we're done. Okay, example 6, solve for x. So here I've got log base 7 of this thing equals log base 7 of that thing. Well, since I have log base 7 here and log base 7 here, well, I can ignore those. I know this part has to equal that part. In other words, I know x minus 3 has to equal 5. So you can see these problems look bad at first, but they're actually pretty simple. Next, I just want to add 3 to both sides, and we get x equals 8. All right. Like I said, these will get harder when eventually we might have to combine a couple logs on one side of the equation, but we haven't learned how to do that yet. So in this section, these types of problems, even though they look hard, they should be pretty easy. Okay, then last one, well, I've already got log base 3 of this thing equals log base 3 of that thing. Well, then I know this thing has to equal that thing. So x over 5 has to be equal to 10. Multiply both sides by 5 to get x by itself, and we get x equals 50. All right, so like I said, these are really the new types of problems today. You might see these are kind of new because the x is in a different place. Okay, but anytime there's one log in your equation, put it in exponential notation. If there's 2 logs in your equation, then you can pretty much ignore the log part and the base. Okay, so the algebra is a little bit tougher in this section, but other than that, nothing too new. Let me know if you have any questions in class.